This is a walkthrough of Problem 3 on Exam 1 of Module 4 in the book Problem Solving Guide for Mechanics and Thermodynamics. Problem 1. We have a 1,000 kilogram car going around a curve at a speed of 25 meters per second. The curve has a radius of 15 meters. It's banked inward at 15 degrees. The frictional force is enough to keep the car going in the circle. Part A, what is the magnitude of the frictional force on the car? Part B, if the frictional force is just barely hanging on to the car, what is the coefficient of static friction? Let's start with the good diagram. There's our car on the bank heading straight into the screen. The forces are gravity straight down, the normal force normal to the surface, and the frictional force is helping the car go in the circle, so that frictional force is in along the surface of the road. Now we have to pick a coordinate system. To make it easy, we pick the coordinate system along the direction of the acceleration. The direction of the acceleration is horizontal, towards the center of the circle in which the car is moving. So with that choice of coordinate system, the sum of the forces in the y direction is 0, and the sum of the forces in the x direction is mv squared over r. Now we have a lot of math to do. So let's treat the car as a point mass and get the angles each vector makes with the coordinate system. So there's our new force diagram, and the road is banked inward at 15 degrees, so the 15-degree angles are right there for the normal force and right here for the frictional force. Some think you should always use the angles the vectors make with the x-axis. I don't think that's a good idea, but let's do it anyway. So let's use the 75. We might as well. So now we have cosine is the cosine of these angles will give the horizontal components. Before we do the math, let's pause and think about the forces. In the upper direction, we have Fn sine 75. The opposite sine 75, of course, if you like, you could do cosine 15. In the downward direction, we have gravity straight down, and then we have this little component of the frictional force, Fr sine 15 degrees. The upward forces on the car balance the downward forces on the car because the car is not accelerating vertically. In the horizontal direction, we have Fn sine 15 or Fn cosine 75 inward, and we have the frictional force cosine 15 degrees inward. These combine to produce the acceleration of the car, mv squared over r. Switching to component view, we just do that. Let's leave the angles off for now. Just use a subscript y and x, and easier to see what's going on there. The force equation in the vertical direction, Fn sub y balances the frictional force in the y direction and the gravitational force. We can put in the angles and we can put in the numbers. So that's the sine 75, that's cosine 75, that's m, and that's the gravitational field, 10 newtons every kilogram, and the weight of the car is 10,000 newtons, mg is 10,000 newtons. That's about all we can do with that. Now we go to the horizontal direction. The x component of the normal force plus the x component of the frictional force are ma sub x, and that's mv squared over r. Our reward for choosing the x-axis horizontal is we get to plug in v squared over r for a sub x. So now those are the angles involved, and then we can put in all the numbers. We have the speed, we have the mass, we have the radius, and we can multiply out that right-hand side, mv squared over r, and we get 12,500 newtons. That's ma of the car. And it's in the horizontal direction, inward, towards the center of the circle. So now we have two equations, two unknowns, Fn and Fr, and we have two. The equations come from the horizontal and the vertical, so we'll solve for Fn here. Subtract Fr 0.9659 from both sides, divide by 0.2588, and we get this expression. That's what Fn is, and we can substitute this expression into the vertical force equation. So here's the vertical force equation, and we're going to substitute the expression in for Fn. There it is, and now we have one unknown. So So we just multiply out this left-hand side, collect the FR terms, subtract 10,000 from both sides, 10,000 newtons from both sides, and we can get FR, 9485 newtons, which is a lot bigger than I drew it on the diagram. I would round this to about 9,500 newtons. So this car is really flying around this curve. It needs a lot of frictional force to keep it going in a circle. My diagram is not to scale. I'm going to have to correct that later if I'm going to try to add those forces. So on to part B. What is mu sub s? We are told the static frictional force is at a maximum. So if the car goes a little bit faster or hits a slippery patch, it's wiping out. When this is the case, the static frictional force is equal to mu static Fn. So we have to calculate Fn. We have an expression for Fn, here it is, and we have Fr now. It's 0.9485, so we can, or 9485 newtons. So we can stick that in and we can calculate the normal force is 12,900 newtons, which is bigger than the weight of the car. Weight of the car is 10,000 newtons. We can now use the frictional force and the normal force to calculate mu static, and we get 0.735, which is a reasonable number for mu static. So now we're done with the problem, but let's add the forces to see if we can get Ma. F gravity is 10,000 newtons, straight down. The frictional force was 9485 newtons. The x component of that is multiply that by cosine 15, we get 9160, which is huge. So 9160 in the y direction, 2460 down, so multiply by sine 15. There's that force. Now we can look at the normal force. The normal force was 12,900 newtons. Sine 15 will give us the inward component, or cosine 75, either one. The upward component is 12,460, and there it is. So now we can think about what's going on in the y direction. We have 12,460 newtons up. Down we have 10,000 and 2,460. So that is good news. The force is balanced in the y direction. In the x direction we have 3340 and 9160. And if we sum those up, we get 12,500. And that is Ma sub x. Good news.